Hello everyone, welcome back to the DSA series. Today we're going to be implementing a linked list in C, specifically a single linked list. There are other types of linked lists such as double linked list and circular linked list. If you guys want me to cover implementation videos on them, you guys can leave a comment down below. Also, if you guys don't know what are linked lists, you can check out the video that I made, which will be a link in the description, and also it will pop up as a card on the screen. So let's start implementing our single linked list. So let's do vim singly linked list.c, and let's start by including our standard input-output library and our stdlib.h, because we're going to be doing memory allocation and stuff. So let's start by simply defining our linked list structure. So we'll start by doing a type def struct linked list underscore t. So a linked list, guys, it simply contains nodes, and each node is linked to one another. Now each node contains a value, and it contains also a pointer which points to the next node, which contains a value which points to another node, and so on and so forth. So we'll simply, in our structure, we'll simply have a int value, and we'll have a struct linked list pointer next, which will be our next node. So we'll then need to create a node for our linked list. So let's create a simple function that we'll use to create our linked list. So it will be of the type linked list t pointer, and we'll call it linked list underscore create node, and it will accept a int value. And we'll do a linked list underscore t new node equals to malloc size of a linked list underscore t. So that way we allocate a pointer to that node on the heap, guys. Now for each node, guys, we'll need to set the value of that node. So we'll say new node value is equal to our value. Then we'll say new node next equal to null. So that node doesn't point to nothing. And then we can simply just return our new node. Now guys, a linked list contains basic operations like insertion and deletion. So let's start by implementing a simple insertion function. So we'll have a void linked list underscore insert front, which will allow us to insert to the beginning of our linked list, or the start of our linked list, and it will accept a linked list underscore t pointer head, a double pointer to our head, and then it will accept a value that we will insert at the beginning. So simply, guys, to insert at the front, we'll simply need to create a new node. So we'll have a linked list underscore t pointer new node, and we'll call our linked list underscore create node function, and we'll pass in a value there. We'll then need to set our new node so that it points to our old head, or the old beginning of our list. So we'll set our new node next equal to our dereferenced head. We'll then need to modify the head, guys, so that it points to our new node, which will become our new head. So therefore we'll dereference our head and we'll set it equal to our new node. So that is our insert front operation. So guys, let's test it out, but before we do that, we'll need to create a few functions. Right, let's create one to print out our linked list so we can display it, right? So we'll have a void linked list print, and it will accept a linked list t pointer head. And to print out our linked list, we'll simply traverse it. So we'll do a while head. So while our head node is not equal to null, we'll set our head pointer equal to our head next, which is our next node. And then each time we're doing that, we'll just say printf modulus d, comma head. Now to show that it links, guys, we'll say if our head next, meaning if it is not null, we'll do a printf, and let's print out a space and the arrow, and then at the end we can just print out a new line. So now, guys, let's create our main function, and let's create our linked list. So we'll do a linked list t pointer, let's just call it linked list. We'll set it equal to null, and then we will call our linked list underscore insert front function, which will accept a pointer to our linked list and a value that we want. So let's say we'll insert 2, and then let's insert some more stuff. So let's duplicate this. Hold on. You let me just duplicate this. So we'll insert 2, then we'll insert 4, then we'll insert 6, then we'll insert 8, and let's insert 10 for the last element. And let's call our linked list print function to print out our linked list. Now, guys, there's one thing we can't forget to do. We allocated memory on the heap using malloc. So that means we need to free our memory so that we release it back to the operating system. So we'll create a void linked list underscore destroy function, which will accept a linked list t pointer head, and it will simply, so we'll need to have a linked list t pointer reference, and we'll dereference the head of our linked list. We'll need to traverse our linked list and free each nodes one by one. So we'll say while ref, we'll say linked list underscore t pointer, let's just say next node is equal to our reference next, and then we can simply just do a free ref. So we free the memory and release it back to the operating system. Then we'll simply say ref equals to our next node, and that is our destroy function. So then we can simply call our linked list destroy function, and then we pass in a reference to our linked list. So now, guys, let's test it out. So let's compile our code. So let's do a gcc singly linked list dot c dash o singly underscore linked list. So we have an error right here. That's at line 24. Let's see what that is. So it should be our head value. So now we can recompile our code, and then we can execute it. And you guys can see we get 10, 8, 6, 4, 2. And notice, guys, we started inserting 2, then 4, then 6, then 8, then 10. But because it's insert front, it inserts at the beginning. So then everything gets reversed. So we get 10, then 8, then 6, then 4, then 2. Let's implement another insert function, which will allow us to append it or insert at the end of our list. So let's do a void linked list underscore pushback function, which will accept a linked list t pointer in head and a int value. So simply we'll need to create a new node. So we'll call our linked list underscore create node function, which accepts a value. And let's see, we'll need to Now to insert at the end of our list, guys, we can't simply do that. We'll need to traverse our list by going to the last node so that we can set the next pointer or the next node for it, which is our new node, right? So let's do that. So we'll need to have a pointer or reference to the head of our linked list. And we'll say while ref next, we'll say ref equals to ref next right here, and then we'll just say ref next equal to our new node. Now guys, here's the thing. If we simply do a pushback into our linked list and we just do all of this, let's say our linked list is empty, our program will literally get a seg fault because we're gonna be dereferencing a null pointer. Now let me demonstrate this to you guys. So I'll do a linked list underscore pushback and ampersand linked list, and let's insert a value of 2. Let me just comment this out, and you're gonna see we get a segmentation fault. So you see we get a seg fault. So let's fix this. So simply before we insert at the end, we can do a if statement right here. We can say if not ref, meaning if our head is equal to null, then we can just simply say head, we can dereference our head and we can set it equal to our new node. Then we can just return from our pushback function. So let's test it out now, guys. So you guys can see now it no longer gets a seg fault and we get our value of 2. Now let's actually compare our pushback function with our insert front function. So let's rename all of this to L1, which is our linked list 1, and we'll have a L2, which is our linked list 2. And yeah, let's just rename this to L1 linked list destroy ampersand L2. And let's duplicate our pushback function, guys, so that it matches this. So instead of linked list, we'll make this be L1, and then we'll make this be L1 again. So L1, this should be L1, and this should be L1 again. And then we need to insert 2, then 4, then 6, then 8, then 10. So let's do a comment up here. Let's say this is pushback. So this is linked list 1 pushback, and this is linked list 2 insert front. And then we can make this be L2. So let's replace all of this with L2. So this should be L2. And now, guys, we can literally start comparing our linked list. So we'll simply do a printf right here, and we'll say linked list 1 pushback colon new line, and then we'll do a linked list underscore print L1. We'll then do a printf linked list 2 insert front new line, then we'll do a linked list underscore print L2. So now let's test this out now, guys. So we can recompile our code and then let's execute it. So you guys can see our pushback function actually inserts at the end, right? Or in the order that we inserted in, right? So you can see we get 2, 4, 6, 8, 10, and our insert front just reverses this pushback thing, which since we're inserting at the beginning, so we get 10, 8, 6, 4, 2, even though we started inserting 2, 4, 6, then 8, then 10, right? So now guys, that we have compared that, let's start implementing a remove function or deletion function to remove a value. So let's do a void linked list underscore remove function, linked list underscore t pointer head in the value, and it will simply remove a value from our linked list. So to do that, we can simply say we need to get a reference to the head of our list, right? So we'll have a linked list t pointer, let's just call it ref, and we'll dereference our head right here. We'll then say if or ref, so we'll need to check our head pointer to ensure that it is not null. So we'll say if ref and ref value is equal to the value that we actually want to remove, then we can simply say linked list underscore t pointer. Well, let's go up here and define a pointer up here. Let's just call it next node, and we'll set it equal to null. And we'll then say if ref is not null and our reference value is equal to the value we want to remove, then we can simply do a free ref. But before we do that, we need to save our next pointer. So we will just say next node is equal to our reference, let's say is equal to our reference next. So we get our next node. Then we can simply dereference our head pointer and we can set it to point to our next node, so that it will essentially remove a value from the front of our list. Now let's make it so that it works for anywhere within the list. So we'll do something right here. We'll say while ref next, we'll say ref equals to ref next, and we'll do a check above here. We'll say if ref next value is equal to the value that we want to remove, then we'll essentially, let's see, we'll save, let's define a new pointer. Let's just call it we can just simply use our next node Yeah, let's just use our next node. We can just say, actually let's define a new pointer. So we'll say target is equal to null. And then whenever we find our value by checking our reference next value, then we'll set our target equals to our reference. Now guys, the reason why we're checking the next value instead of the ref value is because we'll need to get the pointer before, or the node before, the value that we want to remove, because we'll need to unlink our next node so that it points to any other values that comes after our target node, or our node that we want to remove. So after we set our target equal to our reference, we can simply break out of this loop. Now we can do a check right here. We can say if not target, meaning if we did not find the value that we want to remove, we can just simply return from our function or remove function. But if we found that target, we can simply say target. So we'll get our target, and our target is simply the value before or the node before the actual value that we want to remove. So therefore we can just simply say something like next node is equal to our target, and let's see, so target is equal to our reference. So our target, guys, we'll simply make it equal to our reference next. And then we can say if not target, then we just return. And then we can simply say our next node will be equal to our target value next. So that way we'll get the next nodes that come after the value that we want to remove. Then we can simply get our current reference, which will be the pointer before the value that we want to remove, and we can say ref next is equal to our next node. And before we do that, we need to free the memory for our target node. So we can simply do a free target right here. And then we can relink the next pointer to be equal to the next node. So that will be our linked list remove function. So let's test it out now, guys. So we'll do something like, let's define an array. Let's just call it int removal list. And we'll put some values in here that we want to remove. So let's put like 4, 7, and then 10. And we'll just say for size t, removal count is equal to the size of removal list divided by the size of a int. We'll then iterate through a removal list by doing for size t equal to 0 is less than or removal count I++. We'll then say printf removing modulus d from linked list 1 new line, and then we'll call our linked list underscore remove function, which accepts a reference to our linked list 1, so $l1. Then we'll pass in our removal list at index I. Up here we need to also pass in our removal list at index I as well. And then we can print out our linked list 1 again, so we'll say printf linked list 1 after removing values, and then we can just call linked list underscore print L1. So now let's test out our single linked list. So guys, you can see we said removing 4 from linked list 1, and this is our linked list 1. So we remove 4, so there is 4, and then we removed 7. 7 does not exist, so it doesn't remove it. Removing 10, it doesn't remove it. And you guys can see we have 2, 6, 8 right here. So let's say we add a value like 6 to our list. Notice we have 2, 6 right here. If we recompile our code and then we execute it, we get 2, 8 instead. So our removal operation is working. Now let's test it on our insert front operation, which is our linked list 2. So I'm simply just gonna copy this loop right here. So simply copy this. And I'll simply just paste it in again. So this will be linked list 2. And we can change this to L2. And we can print out L2. So now guys, if we recompile our code and we execute it, we get a seg fault for some reason. Why is that? Removing 6 from linked list 2. Why is that? So we said removing 6 from linked list 2, moving 4 from linked list 2, 7, 10, and we get a seg fault. Let's see. Wait, where did we get that seg fault? Let's open up GDB, singly linked list. GDB./singly linked list can run. Okay, typing in our remove function. Let's see. So we check our head first, guys. We then say if it's at the beginning, we set our next node. Oh, that's because we forgot to return from our remove function, guys, before. So that is why the crash is happening. So if we recompile our code, then we execute it, you guys can see our remove function actually works. So this is for our list 2, right? So this is list 2 up here. And if we remove 6 from our list 2, it should disappear. Then we remove 4, it should disappear. 7, it doesn't exist, so it will not disappear. We remove 10, and you guys can see it removed it. So then we're left with these two values, 8 and then 2. So thank you guys for watching. This will be it for today's video, and I'll see you in the next episode.